Well, hello everybody, Dave here, and this is the final lesson in a series of lessons on thermodynamics. In this lesson, we're going to talk about heat engines and their relationship to the second law of thermodynamics. Before we get started, I'd like to remind you the last lesson in which we learned the first law of thermodynamics. When we talked about this, we also talked about the various thermodynamic processes associated with an ideal gas. We came up with four fundamental ones in isobaric, adiabatic, isovolumetric, and isothermal, and the big key to that lesson was to remember what remains constant, what changes, and how does that affect the overall internal energy of the system. If you take a look at the diagram, you can see that we start off with this hot reservoir. If you remember, when we refer to a reservoir, we mean that something that has such a high heat capacity and is so large that its interaction with the engine does not effectively change the temperature. The heat will then flow from the hot element to the engine, and once it's inside the engine, it's going to produce whatever work the engine's required. And then the exhaust of this engine is going to go out to whatever a cold reservoir is, and in that process it will be condensed or whatever needs to be done in order to start the process again. If you flip this over and add work to the system, instead of a heat engine, you'd actually have something like a refrigerator. So if we take a look at this according to the first law, because the working substance goes through this cycle, we know that it's always returning to its initial thermodynamic state. Because of that, the change in internal energy has to be zero. That gives us the idea that the net heat, which in our case is going to be whatever comes from the difference of the hot heat and the exhausted heat, is going to be equal to the amount of work done by the engine. You'll remember that when we define the first law of thermodynamics, the work quantity has a sign convention such that it is the work being done on the system. But in this case, we don't want to talk about the work being done on the system. We want to talk about the work being done by the system. Hence, the equality of negative work is equal to the work being done by the engine. And what this does is it gives us our equation of the work being done by the engine is equivalent to the net heat, or Q hot minus Q cold. Now, you might notice that we have absolute value signs around it. Q can be either positive or negative, and so as long as we have these absolute value signs, we take care of that potential sign issue. It is worth, of course, remembering that if we have a PV diagram of this cyclic process, the work done by the engine will be the area enclosed by the processes. We dealt with this in a previous lesson, so make sure we remember that. The other quantity that's going to be highly useful when discussing engines is thermal efficiency, which is basically telling us how good our engine is at converting the input heat into the mechanical work or whatever kind of work we want done by the engine itself. You'll notice that if we substitute in the equation for the work done by the engine, you can simplify this equation into 1 minus Q cold over Q hot. Notice again the absolute value signs so that we don't have a sign mishap when we actually do the mathematics. As mentioned previously, what we can do one way, we can also do the other when it comes to a heat engine. And if we do it in reverse, what we see is we can actually have a refrigerator, or what's known as a heat pump. And the basic idea behind this is we have this interaction between a cold reservoir and the heat pump, but this time we're actually putting work into the system, or work being done onto the heat pump. And what happens is it will now exhaust this new heat at a higher temperature than what it came in. This is a classic example of a modern day heat pump for houses. It's also a representative of a refrigerator. So let's go through the processes involved with a refrigerator. We start off with a refrigerant going through an expansion valve. And when this happens, work's being done by the refrigerant so that the internal energy of it is going to be lowered. We know from previous exposure to equations that the change in internal energy is directly related to the change in temperature. So if we can do work such that the internal energy is lowered, that has to lower the temperature of the refrigerant itself. From there, there's a heat exchanger process by which the warmer air inside the refrigerator interacts with the colder refrigerant, and energy is removed from the air inside the refrigerator so that the overall result is a cooler temperature inside the refrigerator. From there, the refrigerant is sent through a compressor. such that we are actually doing work on the refrigerant now to increase the internal energy of it. So that the next step, when it's on the back, on the outside of the refrigerator, there is now this exhaust capability of the refrigerator, so that the refrigerant, being a higher temperature than the surrounding environment, is exchanging that energy out into the environment. If you've ever put your hand on the back of a fridge or even been close to it, you'll notice that it's quite hot. The reason for that is exactly this process. It is being exhausted into the environment. If we want to talk about the effectiveness of a heat engine, then we would be referring to the coefficient of performance. The coefficient of performance is the ratio of the amount of heat drawn in from a given reservoir divided by the work being done by that machine. So you can see that there's a difference between a cooling mode and a heating mode in whichever reservoir the energy is being extracted from. In general, the larger the ratio, the better the performance. However, we do know that there's a limit to this, because we know that there is no heat engine capable of taking all of this heat absorbed in from the reservoir and convert it into whatever energy is required for the engine itself. This is actually one of the first statements of the second law of thermodynamics. If we start playing around with the way that we're wording these laws, we can think about the first law of thermodynamics as we cannot get a greater amount of energy out of a cyclical process than we put in. That was based upon the idea that delta U is equal to 0. If we think about this in the same regard, then the second law of thermodynamics can be stated as we can't break even, in that you can't take energy from a reservoir and convert 100% of that into the energy that you're looking for out of an engine. Another way we could state the second law is that if two systems are in thermal contact, the net thermal energy transfers spontaneously by heat from the hotter system to the colder system. So hopefully you've heard this before, in that when you have two objects touching together, the energy has to transfer from the hotter element to the colder element. And if we want to go the opposite way, we're going to have to do work to make that happen. That was the essence of our discussion of a refrigerator. The quantity of entropy is very much associated with the second law of thermodynamics. And in definition, it's the quantity to measure disorder. So you can imagine the other state variables associated with a gas. We had pressure, we had temperature, we had volume. Well, entropy is another one of those state variables. And so if we want to find the change in entropy during any constant temperature process connecting the two equilibrium states, it can be defined by delta S being Q over T, where Q is the heat inputted into the system and T is the absolute constant temperature, in this case the reservoir by which we are extracting the heat from. We know from experience that this can be a positive or negative value depending upon how you're looking at it. When we see an object becoming less random, it's only because another object is becoming more random. An interesting derivation to do for this now is imagine a small amount of heat flowing from a hotter system to a cooler system. If we find the change in entropy, then we would have to take the sum of the change in the entropy associated with the hot reservoir and the change in entropy associated with the cold reservoir. But something interesting happens. We know again, because we are extracting heat from the hot reservoir, that the entropy would decrease. So if you notice, we have a negative sign on Q over T. However, this is causing an increase in the entropy of the cold system, and the result that we get is a positive Q over T. But now something interesting happens, because we know that the hot temperature is larger than the cold temperature. Well, that means that if we look at these fractions, the actual magnitude of Q over T hot has to be less than the magnitude of Q over T cold. And what that means is, even though there is a decrease in entropy in one end, the increase in the colder system's entropy is larger than the decrease of the hotter system's entropy. We can generalize this according to the following statement, that the change in entropy is greater than 0 in all irreversible processes. And this, my friends, is actually one of the primary statements about the second law of thermodynamics, is that the entropy of the universe never decreases. There was a statement that I learned in university that was, the universe wants two things: to be as random as possible and to be as cold as possible. And this is the statement of its randomness. So it's interesting that we brought up this idea of being irreversible. It means that we need to define what a reversible process is. And reversible, by definition, is one that doesn't violate the laws of physics when it's done in reverse. You can imagine looking at something happening in real time forwards and then pausing and rewinding it, and what you observe could be as physically possible as it was when it was going forward. So the reversible process means that something like billiards balls colliding is absolutely a reversible process, in that if it's perfectly elastic and there's no friction present, then we wouldn't be able to tell forward or reverse what the direction of that operation was. Another way of stating it would be that in an equilibrium state, the system can return to its initial conditions on the same path in the reverse direction. If you think about this like a PV diagram, if we have a cyclical process in a PV diagram, what a reversible process would be is that we could actually change the direction of the arrows, and we would still be able to get to our initial state that we had originally. If we compare this to an irreversible process, now we can think about watching a book sliding to a stop on a table. If we watch this forward, that makes sense. But if we watch it backwards, physically what that would mean is that friction was causing the acceleration, and it would actually be cooling down the surface of the table as it was accelerating forward. Physically, that doesn't make sense, which means we can consider this an irreversible process. In general, anything that dissipates energy is considered an irreversible process, because not all of the energy can then be turned around. If we watch that in forward motion, then all the physics would make complete sense. But if we go backwards, we would be making statements like friction causes acceleration, and the sliding process actually cools down the object as it moves from 0 to a higher speed. So in that case, that doesn't make sense at all. In general, if energy is dissipated, it will always create an irreversible process, because some of the initial energy has been converted into other forms, and that now is not available to perform the reverse process. So in the case of order to disorder, this can happen spontaneously, but it cannot happen in reverse. One of the interesting properties of entropy is it has a requirement to always have time moving forward. And because of that, we've actually given a name associated with this forward motion of time because of entropy, and it's known as times arrow. When we discuss the efficiency of engines, we always like to compare them to a Carnot engine, which is an idealized reversible cycle between two energy reservoirs in the most efficient engine possible. So there is no losses of energy. It is a reversible cycle, which is, as I've explained through the second law of thermodynamics, an impossible feat at this point. Now, Carnot's theorem states that no real engine operating between two energy reservoirs can be more efficient than a Carnot engine operating between the same two reservoirs. So you'll notice through your studies that we actually have two ways of calculating efficiency. We have the efficiency of a Carnot engine, and we have the efficiency of a real engine, and it should always be that the efficiency of the Carnot engine is higher because it is this reversible process. So keep this PV diagram in mind as we go through the Carnot cycle. The first step is this isothermal expansion from A to B. And I've given you the diagram to show you that we have a cylinder attached to a reservoir at a constant temperature TH. And energy is going to flow from that reservoir into the system, and the result is going to be the piston will go up. If we remember our sign conventions from the last lesson, then we know that we can consider this either negative work being done on the gas or positive work being done by the gas on the piston itself. From there, we get into the idealized version of the Carnot engine by replacing the hot reservoir with a thermal insulation, which stops the exchange of heat between the cylinder and the outside environment. Even though this has happened, there is still going to be a natural expansion of the gas, but now it's going to be done adiabatically in that the work is still being done by the gas on the piston to raise it up, but now the temperature of the gas is going to change from the temperature it had from the hot reservoir into a different temperature, which we'll call T cold. Now we go to the third process, which is an isothermal expansion. The piston has made it to the top of its reach, and we replace the thermal insulation with a cold reservoir of a temperature that's colder than the gas. What will now happen is the gas being in thermal contact with this is going to exchange heat towards the cold reservoir, which is going to cause this isothermal compression of the gas itself. If we talk about this again in terms of sign convention, we can talk about this as being positive work being done on the gas because of the decrease in volume, or negative work being done by the piston. And to finish the Carnot cycle, we do an adiabatic compression by replacing the cold reservoir with the thermal insulation yet again. And in that process, the gas will continue to compress, but it will do so adiabatically because there is no energy exchange with the outside environment. And the result will be, again, negative work being done on the piston or positive work being done on the gas. If we want to calculate the efficiency of the Carnot cycle, we can simply take 1 minus the temperature of the cold reservoir divided by the temperature of the hot reservoir. You'll notice that this looks similar but different to the equation for efficiency of real engines, but you have to remember that with real engines, we're dealing with an energy dissipation that Carnot cycles just don't have. They're a reversible process. It might be interesting to note that a Carnot cycle cannot be 100% efficient either, and that may not make much sense based on the idea that we're a reversible process where there's no energy dissipation. However, if we quote the third law of thermodynamics, the third law states that it's impossible to reduce the entropy of a system to its absolute zero value in a finite number of operations. Well, because of that, that means that we can never take Tc down to absolute zero, so there will always be some fraction of Tc over Th that we have to subtract from this value of 1. So the efficiency of a Carnot cycle can be highly efficient, but it can never, by the laws of thermodynamics, be 100%. So everybody, that's the end of our lessons on thermodynamics. We focused a lot on the theoretical end of heat engines and heat pumps and refrigerators and Carnot cycles in this lesson. However, in the previous lesson, we did learn all the mathematical principles associated with isothermal and adiabatic processes and the various other thermodynamic processes that we covered. So I encourage you to take another look at that lesson, make sure we're clear on that, and then approach all your various practice problems. We'll see you again.